Hello DTIP attendees. I am Laurent Latorre from University of Montpellier in France. This presentation concerns the development of a low-power audio recorder making use of MEMS microphones. This is a joint work with Simon Chamaillet-James. Simon is an ecologist working with the CEF laboratory, which is in the same city of Montpellier in France. About the context. Well, research in the ecology field has been using technologies such as GPS or IMUs for quite a few years now. You've probably seen maybe on TV those collars here that are used to track wild animals. Still, data obtained from these sensors, so basically it's a location and some movements, do not provide everything the ecologist might need. First, the mapping between GPS or IMU data to some unusual activities is quite impossible. In addition, behaviors include voicings, and those are not always associated with any gesture. And finally, with such a GPS collar, you know that the zebra is running, but basically you don't know why he's running. He might be running in response of an audio input corresponding to a danger, for instance. Graphs here illustrate what audio can bring. Here, from the foraging sounds, we learn when zebras are most likely eating within a day. Here. And there, we record snort noise, and this noise is an indicator of the well-being. So we can say from this result that zebra feel better around noon. So as you can see, audio brings useful information with a data volume that we can keep low, especially when compared to video, for instance. And low data volume is good for autonomy, and it's good for further post-processing of the recorded data. To keep it small and low cost, we've considered using MEMS microphone like those we all carry in our cell phones. There are literally hundreds of references with different audio performance, packaging, or interfaces. We've retained 3 devices from ST, InvenSense, and Knowles. You can see that audio quality in terms of signal over noise ratio is pretty much the same for all the MEMS microphones. Differences are mainly the output format, which can be either analog from those one or digital. Digital format is basically a pulse density modulation coming straight from a sigma delta ADC modulator. So as you can see, and this is usually the case, the power consumption is lower with analog microphone, but somehow you will have to implement a conversion stage at some point, and on the system level, all those solutions are pretty much the same in terms of power consumption. So the InvenSense was chosen because it has an extended low frequency response down to 6 Hz, which is good for elephants that use infrasounds. And the Knowles microphone was retained because it is waterproof. Digital microphone provides the best integration capability because basically you need nothing to interface the microphone with the digital world. Considering analog microphones, you need an ADC. Most of time, you have ADCs available in the application microcontroller, but those have limited resolutions, and if you plan to use it, you'll need some anti-aliasing low-pass filtering somewhere in the analog domain. Filters such as B-quads are quite hungry in terms of power. So instead, we use an external sigma delta modulator and a gain stage to fit microphones with different sensitivities. So doing so, we somehow build something very similar to a digital microphone, both in terms of digital format, because we provide the same PDM stream, but also in terms of power consumption. The price to pay when using analog microphone is additional space on the board, but that's not too much. So having said that, here is the global architecture of our recording device. It is built around a central STM32 microcontroller that collects data from the microphone, from other sensors, if any, and then manage the mass storage, which is an SD card in this case. We also need to communicate with the computer to set up the recorder time and date. That's basically to get the files onto the SD card with the correct timestamps. So this architecture itself is pretty simple and obvious. The interesting part is the use of this DFSDM box here, which stands for Digital Filter for Sigma Delta Modulator, and which is one of the key of the very good power performance we obtain at the end. So I'm going to give some details on that particular function. The DFSDM is an hardware peripheral available in some STM32 devices. It is designed to work with external sigma delta modulators. It provides a clock with a tunable frequency, and it filters incoming data. The filter basically is a low-pass filter that somehow averages the amount of ones in the bit stream and then outputs 24 bits audio samples. The transfer function is given here to show the two parameters that we can play with. One is the oversampling ratio, which is the number of 1-bit samples we want to average, and X is the filter order. For instance, with X set to the value of 2, we got that filter recursive equation here, where an output samples Y is computed using input sample X and both input and output samples from the past. So the global audio performance depends on the clock frequency, on the oversampling ratio, and on the filter order X. The oversampling ratio will determine the audio bandwidth, and X affects the output dynamic range of the filter. To study the effect of those parameters, we've set up an experimental test bench using an audio analyzer. So the audio analyzer provides signals to the loudspeaker, such as single tone or noise. It supplies and clocks the microphone, and in return, it can analyze the microphone bit stream. In the same time, clock and bit stream are also captured by a logic analyzer so that data can be processed offline in a software simulation that perfectly mimic the hardware of the DFSDM module. So doing so, we can extract audio features based on FFTs. Note that I'm introducing here the idea of audio data compression using the ADPCM encoding algorithm. The idea of audio compression came very early in the design for very obvious reason of saving mass storage, or in other words, for the same amount of mass storage, extend the device operating lifetime. Because we are using small CPU, we did not consider complex compression algorithms such as MP3. It would require too much computing capability and power for real-time sample processing. So instead, ADPCM was chosen because it is simple and requires only few operations. The idea of ADPCM is to replace each 16-bit audio sample by the difference between two consecutive samples using a pre-calculated table. So the output is then 4 bits, so it's a 4:1 compression ratio. Easy to implement. First, we study audio spectrums with no compression. In order to measure the SNR, we play a loud single tone at 1 kHz with a pressure level of 90 dB, which is the limit of the microphone linearity. You can see those tones, you can see that tone on the spectrum here and here. So both graphs exhibit the expected sigma delta noise shaping, which is a good news. The first graph shows the effect of the oversampling ratio. As expected, the only effect of OSR is on the bandwidth, with a reduced bandwidth when we increase the oversampling ratio. The second graph shows the effect of the filter order X. So the higher order, the more averaging we do, and the best it is in terms of noise shaping. Although increasing X too much may produce saturation at the DFSDM hardware output, because it also increases the output dynamic range. So there's a limit in the value of X. So with the same audio input, we now study the effect of audio compression with various sample rates. So as expected, the compression algorithm works better with higher sample rates, so with lower oversampling ratios. The reason is that the more sample we have, the best are the difference estimates. But still, even with very low sample rates, down to 12 kHz, which corresponds to 6 kHz audio bandwidth, the quantization noise is kept in the minus 60 dB range, so that compared to the microphone intrinsic noise, there's no significant degradation. I must admit that we can hear it, but it's okay. So compression is okay regarding audio quality. And time has come to discuss the software. So on the left is the whole device state machine. So I'm not going into the details. We have basically startup states in blue. We have setup states in green. We have the standby state in yellow, and the recording loop in red. On the right here are the details of the recording process. So that box here is detailed here. DFSDM receives the microphone samples, and then the transfer to memory is done using a DMA controller, direct memory access. That is, this process is fully hardware and no CPU is involved in this transfer. So during this process, CPU can be in a low power mode. Basically, the clock is off for the CPU. When the first buffer stage here is full, CPU wakes up and then process audio samples to reduce their size. So actual size here is 32 bits, and it is reduced to 16 bits if we do not compress, or 4 bits if we do apply ADPCM compression. And then it is stored into a second buffer stage. When the second buffer stage is full, CPU manage the transfer of samples from that buffer into the SD card. So doing so, we make an optimized use of the available memory. It keeps the CPU down most of the time, and it spaces SD card writing operations. And this is important because writing time onto SD cards are not quite deterministic, and we need some comfortable margin here. And here are the final results. So both graphs represent the transient supply current during the recording loop. One can recognize the three phases process that I just described on the previous slide, with the capture of the microphone samples here, which has the lowest power needs, then the processings a bit higher, and then the storing events, so storing onto SD card, which needs quite a lot of energy. And here is a zoom onto a typical writing sequence, and for this we take an average current for a given amount of time that is used in the next analysis. So this table compares the power consumption with or without audio compression. On one hand, compression itself requires CPU power, but on the other hand, it reduces SD card writing events. So comparing the two cases, we demonstrate that about 30% of energy can be saved using compression. So that's the interesting result of this study. At the end, the global power consumption of our recorder is about 6 milliwatts, which is pretty good compared to other existing products on the market. And that will be my conclusion. I apologize for it to be a little commercial, but I could hardly find research paper to make a comparison. The closest device on the market is the AudioMot from Open Acoustic Devices. It also started as an academic project, and for the same audio quality, our design is 10 times better in terms of power consumption. I also mentioned the song meter, which requires even more power, but for a much better audio quality. But this one is pretty expensive. So we've demonstrated up to 900 hours, that's about 5 weeks, of continuous audio recording with our first prototype here it was built around the Knowles waterproof microphone. Two other prototypes have also been fabricated, one with additional sensors, accelerometer and magnetometer, and another one with the InvenSense microphone to sense infrasounds for applications with elephants. I am done, so thank you very much for your attention.